Alright, so welcome back. One of the things that we did in the previous example was we drew y equals 2 to the x, and we graphed it as a continuous graph, meaning there was no holes in our graph. And there was a subtle thing that occurred in that, in which we actually had to consider the values of y equals 2 to the x when x is, say, an irrational number. Alright, so the table of values we constructed, we used all integer values, right? Whole numbers or negative numbers. Now, we have worked in the past, if we recall, we have worked in the past with rational exponents, right? Where we said that, for instance, 2 to the 1/2 power, you may remember, is the same as the square root of 2. Or if I have, say, 8 to the 2/3 power, that was the same as, we could actually write it as two different ways. That would be the cubed root of 8 squared. And actually a little bit easier way to write it is the cubed root of 8 all squared. So I could square first, or I could cubed root first, and either actually gives me the same result. And the cubed root of 8 in this case is 2, and 2 squared is 4. Where in this case I would have the cubed root of 64 when I square the 8, and the cubed root of 64 is in fact a perfect cube, which also gives me 4. So we have seen fractional exponents before, or rational exponents is another way I could say that. And what we did in that case, I just want to point out that the denominator of that exponent just became the index of the radicand, and the numerator of that exponent remained as an exponent over the base. Alright, so we've seen that before. But one thing that we have not considered, but actually results as a means of drawing that continuous curve, we have to consider what about cases when we have irrational numbers. So I'd be talking about numbers such as y equals 2 to the square root of 3. Alright, and it turns out that they do in fact exist. There is an approximated value for that we'd be able to figure out, and it's actually, if you use a calculator, you'd get something like 3.321999709. Alright, but the point is that those irrational exponents, irrational by the way, are just numbers that cannot be written as a fraction. Alright, and typically numbers, any square root of a number that isn't a perfect square would give us an irrational number. Other irrational numbers we've seen in the past are like pi, right? Anything that has an infinitely long non-repeating decimal is going to be irrational. But it turns out irrational exponents do exist, and all of the same properties of exponents do apply to those as well. So we're just going to consider a couple cases just to see how well we can work with those types of exponents. So for instance, if I have 2 to the, say, 3 square roots of 5 multiplied by 2 to the square root of 5, I'm multiplying two things of the same base. So the property that I'm applying here is the a to the m times a to the n equals a to the m plus n property, right? The product of powers, you would add the exponents. And the same thing actually can occur here. Just because I have irrational numbers, it's not going to affect the outcome. So I'll have 2 to the 3 root 5 plus root 5. And you may have realized that those are in fact like terms. We could think of those as that, where I have 3 square roots of 5 and 1 square root of 5 combining to be 4 square roots of 5. And if I want to, I could actually even simplify the 2 to the 4th part here, where I could just think of 2 to the 4th as being 16, which we actually did on our previous example. So 16 to the square root of 5 is a simplified version of that product, and the property of exponents that we used was the product of powers. We also can use other properties. So for instance, what if I have let's say 3 to the square root of 2 all to the square root of let's say 6. Alright, so the property I'm going to be using here is the power of powers property. So if I have a to the m to the n, the property we used there was that we would multiply those exponents, and that would give us a new exponent. So in this case, I'd have 3 to the square root of 2 times the square root of 6, which simplifies to be 3 to the square root of 12 if I multiply those together. And perhaps you remember that 12 as a radical can be reduced. There is a perfect square that goes into that, which is 4. So 4 goes into it, in fact, 3 times. So root 4 times root 3. And what is the square root of 4? That would be, oh, I think I'm probably going off the page here. I'm going to continue this up here. So that would have been 3 to the square root of 4 times the square root of 3. The square root of 4 becomes 2, so that's 3 squared, or 3 to the 2 times root 3, which I can think of as being 3 squared, right, to the root 3, and 3 squared is 9. So 9 to the root 3 is the way I could simplify that. A more interesting type of result, and actually I do encourage you, pause this video if you need to finish writing this down, but a more interesting type of result is this. And this will actually help us solve some problems later on. What if I have, let's say, 2 to the square root of 2 multiplied by 8 to the square root of 2. Now I can't immediately use this property, a to the m times a to the n equals a to the m plus n, primarily because these bases are not equivalent. However, with some subtle manipulation, we can actually recognize that 8 is a power of 2. I could rewrite 8 as a power of 2. So I could think of this as 2 to the square root of 2 multiplied by 2, and 2 to what power is the same as 8? So let's see, this is the part that I'm replacing. 2 to the third power is 8. So I could now actually rewrite that as 2 root 2 multiplied by 2 to the 3 root 2. And now that I have the same bases, I can now use this property of exponents and add these exponents and put them over the same base. So that would be 2 to the root 2 plus 3 root 2, and I have 1 root 2 plus 3 root 2, right? So I can combine those as like terms, and I would have a total of 4 root 2, and 2 to the 4th is 16, which we saw earlier, so 16 root 2. And we will actually be using this type of property of rewriting this as a power of 2 or as a power of another base within the problem. We can use that even to solve equations, which we will do in later problems. And the main reason we're bringing up this concept of irrational exponents, once again, just to review, had to do with the fact that when we drew that graph, we assumed that it was a continuous curve, all right, that every point was represented there, that there were no gaps, and in that assumption we had to consider, what about when x is irrational? And that's why we're bringing that up at this time. All right, so we'll move on to the next example.